Hi, good morning everyone. So last time we proved the following theorem. Let G be some finite subgroup of the group of automorphisms of a field K. So let G be a finite subgroup of the group of automorphisms of some field K. And let F be the fixed field of G, so the set of elements in K which are fixed by all the elements in the group G. Then the degree of the field extension is larger than the number of elements in the group. Okay, so we proved this last time, that if we have some finite subgroup of the group of automorphisms, and if F is a fixed field, then the degree of the extension is larger than the number of elements in the group. And as a result, we have the following important corollary. Let K over F be any finite extension, be a finite field extension, then for any finite field extension, the degree of the extension is always larger than the number of elements in the group of automorphisms of K which fix F. So in particular, it's part of the corollary that the number of automorphisms which fix F in any finite field extension is finite and has less elements than the degree of the field extension. Okay, proof. So this follows from the previous theorem. Okay, so we have that the group of automorphisms which fix F, this is a subgroup of the group of automorphisms. Now let L be the fixed field of aut K of F. So what we know about the group aut K of F is that all of the automorphisms fix F. So if we take the fixed field, which might be larger than F, but it has to contain F. So we have that L is in between F and K. And it's possible that L equals F, but it's possible it's not. So for example, in one of the extensions we've looked at before, is when you adjoin the cube root of 2, you get that the automorphisms which fix Q is, there's just one, it's just the identity, so in that case a fixed field is everything. Okay, so it is possible that L, for example, equals K. But in any case, a fixed field certainly has to contain F. So now we can apply the theorem. Okay, so by the theorem, K is in between, so L is in between F and K, and we have that if the degree of the extension over the fixed field of our group, which is L, is larger than the number of elements in our group, and our group in this case is ought K over F. So we have this inequality. Okay, but furthermore, what we want is an inequality involving the degree of the extension over F, but this is a product of the extension over L, the intermediate extension, and L over F. Degrees are always positive integers, at least one. So this is greater than K over L, which as we proved is greater than ought K over F by the theorem. So we have the desired inequality. Okay, so now we make a very important definition. A finite field extension K over F is said to be Galois if the degree of the field extension is exactly the number of elements. So we always have the inequality, but if the degree of the field extension is exactly given by the number of elements in the group of automorphisms which fix of K which fix F, if we have the equality here, then the field extension is Galois. Okay, and if it's Galois, then we call this group of automorphisms which fix F the Galois group. So if we have a Galois field extension, then we write gal K over F for ought K over F. So we write gal K over F for the group of automorphisms fixing F and we call it the Galois group. Of the field extension. Okay, so let's do some examples. So let's go back to the two examples we've looked at earlier. So we saw that there are two elements, if we look at in the automorphism group, of the field extension Q root 2 over Q. So the two elements are the identity as well as the element sigma, which is the automorphism taking a plus b root 2 to a minus b root 2. Okay, so we have two elements, and the degree of the field extension is 2, because the minimum polynomial for root 2 has degree 2. So this extension is Galois. Okay, for another example, we can look at Q adjoining the cube root of 2. And this is not Galois because the automorphism group is just the identity. Because we saw that, so other than the identity, right, the issue is that the minimal polynomial for cube root of 2 has one real root, the cube root of 2, plus two imaginary roots. And since any automorphism has to permute the roots, other than the one, any automorphism which is not the identity would have to take the real root to something which is not real. And this is not possible for an automorphism of Q adjoining cube root of 2 because that's a subfield of the reals. Okay, so this is not Galois since, as we've seen, automorphisms of the field extension just has one element, the identity. But the degree of the field extension is 3 because the minimal polynomial has degree 3. But okay. Okay. So in the rest of the lecture, our main goal is to actually improve the theorem from last time. So we're going to actually prove something I alluded to last time, which is that in the theorem itself, we actually can have an equality. Okay? So let's write down the following theorem. Let K be a field. Let G be a subgroup of the group of automorphisms. So let G be a finite subgroup. Then if we take the fixed field for G, we actually have that the degree of the field extension, K of F, is exactly equal to the number of elements in G. So it's an improvement of the theorem that we proved last time. Okay, but so the book puts these two theorems together, but as a result, the proof is extremely long in the book, so I decided to split them up since it's in any case more natural to split them up. In any way, you only need sort of 1/2 to make the definition of a Galois field extension. Okay. So we're going to prove that, so if we let F be the fixed field of G, then the degree of the field extension is equal to the number of elements in G. Okay, proof. So let's, the group G has to contain the identity. Let's say that the elements of G are sigma 1 up to sigma n, where n is the number of elements in a finite group, and let's make sigma 1 the identity. So we proved in the previous lecture that degree of the field extension is larger than the number of elements or equal. So we proved on Monday that the degree of the field extension is at least G. Okay, we want to prove equality here. So suppose for a contradiction, that the degree of the field extension is strictly greater than n. Okay. Then in this case, I can take n plus 1 elements in K which are linearly independent over F. So in this case, there would exist n plus 1 elements alpha 1 to alpha n plus 1 of K, which are linearly independent over F, since the degree of the field extension is strictly greater than n. Okay, so then consider now the system. So consider the following system of linear equations. We have our n elements, sigma 1 up to sigma n of the group, and I'm going to use these to build up a system of n equations in n plus 1 variables. So we look at the system. So we have n elements in the group, and we have n plus 1 elements in K, which are linearly independent over F. So now we kind of put things together and we look at the following system of linear equations. We take the first element of the group, sigma 1, which is actually the identity. Then I plug in alpha 1 and introduce a first variable, x1, plus sigma 1 alpha 2 x2 plus sigma 1 alpha m plus 1 x m plus 1 equals 0. That's my first equation. It involves n plus 1 variables, x1 up to xm plus 1. And I now repeat this going through all the elements in the group. Sigma n alpha 1 x1 plus sigma n alpha 2 x2 plus sigma n alpha m plus 1 x m plus 1 equals 0. So this is a system of n equations, where n is the number of elements in the group, in n plus 1 variables, x1 up to xn plus 1. Oh, and these are linear equations. And let's call my system of equations star. Okay, so, well, this is similar to the proof of the theorem proved on Monday. We have more unknowns than equations. Each equation reduces the dimension of the space of solutions by at most 1, and we only have n of them. So the dimension of a solution is at least 1. Okay, so the number of unknowns is strictly greater than the number of equations. Therefore, there has to be non-zero solutions. So this system has a non-zero solution. Actually, has at least a one-dimensional space of such solutions. Okay, so amongst all the solutions, choose one with the least number of non-zero coordinates. So amongst all the non-zero solutions, choose one solution let's write our solutions as y1 up to yn plus 1 with the least number r of non-zero coordinates yi. So after, without loss of generality, after sort of renumbering everything in the setup, we can assume that the non-zero coordinates are y1 up to yr. So without loss of generality, we can assume y1 up to yr are the non-zero coordinates because there was no, because we can just by symmetry in the setup. So after renumbering, we can assume y1 up to yr are the non-zero coordinates. So up to renumbering in the variables and in these alpha 1 up to alpha n plus 1. So after doing a reordering of those elements and therefore in the variables, I can assume that y1 up to yr have a non-zero coordinates. And next, note that since all equations are linear, if y1 up to yn plus 1 is a solution, then since all the equations are linear, right, so is c times y1 up to yn plus 1 for any c and k. So in particular, I can pick any element and I can divide by it, any non-zero element, and divide by it to get a new solution. Okay, and we know that yr is non-zero by definition. So we can divide by yr to basically assume that yr is, which we know is non-zero, to basically assume that yr is 1. Okay, so we can get our solution, which has a minimal number of non-zero entries, and it has the form, we can assume y1, yr minus 1, and then we can assume the last one is 1, and the rest is 0. And this is a solution to star. Okay, and the last thing to notice is that at least one of the first r minus 1 terms is not in F. Okay, so otherwise, if y1 up to yr minus 1 were in f, then all the terms, and the only other terms in the solution are 1 and 0, which are also in f. So then I could sub this back into the first line of star. So in subbing back into the first equation, for star gives, since, here's our equation. If I now sub my solution in, then, well, don't forget that sigma 1 is the identity. So it now reads, once we sub in the solution, alpha 1 y1 plus alpha 2 y2 plus alpha r minus 1 yr minus 1. Yr is 1, the rest is 0. So let's just not write this one. Okay, I've just subbed it back in, and I haven't forgotten the sigma 1 is the identity. So I get this equation, but this is now an equation with coefficients in f. So these guys are all in f. And this contradicts that alpha 1 up to alpha r are assumed linearly independent over f. Okay, so I can assume at least one of the y1 up to yr minus 1 is not in f, and without loss of generality, we can assume that y1 is not in f. So after renumbering, we can assume y1 is not in f. Okay, so the first thing to remark is, let's sub our solutions into the equations. Then we get the n equations sigma I alpha 1 y1 plus sigma I alpha 2 y2 plus sigma I alpha r minus 1 yr minus 1 plus sigma I alpha r yr is 1, so this equals 0. So we have these equations where I runs from 1 to n. Let's call this 1. Okay, and we're assuming y1 is not in f. Let's use that fact. So since y1 is not in f, which is a fixed field, so since y1 is not in the fixed field of G, there must be some element which doesn't in G, which doesn't fix y1, because if every element fixed y1, then it would be in a fixed field. So there is some sigma L which doesn't fix y1. Otherwise it would be in a fixed field if every element in the group fixed it. So there must be some sigma L in G with sigma L not fixing y1. Okay, so I can now apply it to the equation 1, using it as a homomorphism. So if I apply it to the equations 1, I get sigma L times sigma I alpha 1 sigma L y1, which is just y1, plus sigma L sigma I alpha r minus 1 y r minus 1 plus sigma L sigma I alpha r equals 0. For I equals 1 to n. Okay, and this first element, sigma Ly1, is not y1. So let's call this 1 star. No, that's not, actually that's not. Okay, so the first thing to observe, right, is since we're dealing with a group, then these elements I've got lying around, sigma L, sigma 1, sigma L, sigma n, these elements in the group are just a permutation of the original sigma 1 up to sigma n. So the elements that you get in the group, once you apply, if you apply some sigma L to, and look at all the products in the group, well, that's an invertible operation, because I could also apply, since I'm in a group, I could then undo that by applying sigma L inverse. So this is just a permutation. These elements are just a permutation of the original elements in the group. So in particular, there is always some j such that sigma L composed with sigma I is sigma j. So I can always let j be some variable such that sigma j equals sigma L over sigma I for hi. And then, well, now let's call it 1 star. So then 1 star then this system of equations, well, let's rewrite it. Using it as a permutation, I can rewrite each of these entries sigma L composed with sigma j, sigma I as sigma j for some j. And it's going to look like sigma j alpha 1, where j is this index, where such that sigma j equals sigma L composed with sigma I, sigma L y1, just subbing for this sigma j for these guys. Right. Let's erase this so it's not there in the lecture notes. Plus sigma j alpha r minus 1 sigma L y r minus 1 plus sigma j alpha r equals 0. And now j, since applying the sigma L to the sigma i's just gives us a permutation, j still runs over 1 to n. Okay, so now I've got this system of equations for j running over from 1 to n. But j is just a dummy variable, so I could actually relabel it back to I. But it's the same thing. So j is just a dummy variable here when I'm looking at this system over j running from 1 to n. It makes no difference what symbol I use for it. So it's the same as writing the same thing, but I'm going to write my dummy variable as I again. And I'm going to call this system of equations 2. So now I've got two equations, two systems of equations. I've got this equation 2, and I've got this the original equation 1, and I can now compare them. So I can subtract 2 from 1. And then I get the following system of equations. So the last one cancels now, right? So the last term, sigma I alpha r, is common to both, and it cancels. So it's now a system up to sigma I alpha r minus 1. The half terms now cancel, right? So I just got r minus 1 non-zero terms. Y r minus 1 negative sigma L y r minus 1 equals 0. Okay, well, therefore, so this is true for all I. Therefore, we see from this, right, by definition, y1 minus sigma L, y1, yr minus 1 minus sigma L, yr minus 1, zeros elsewhere, is also a solution to the system of equations. And it's non-zero. So this wouldn't mean anything if it was just 0. 0 is always a solution. So I should ensure before I make any conclusions that this is non-zero. But it's non-zero because, because we know that y1 is not in the fixed field. Because y1 is not equal to sigma Ly1. So it's non-zero. And it has at most r minus 1 non-zero entries. So it has strictly less than r non-zero entries, which contradicts the fact that r was a minimal number of non-zero entries. This is a contradiction. Since r was the minimal number of non-zero entries. Okay, and with that, the proof is complete. So let's just end this lecture with a nice corollary, an important one, I should say. So take some finite field extension, then it's Galois as long as the fixed field of the automorphism group is precisely f. So then take some finite field extension k over f, then K over F is Galois if F is the fixed field of the group of automorphisms of K over F. Well, this just follows now from the theorem, so proof. So if F is a fixed field, then I can just apply the theorem to get the degree of the field extension is equal to the number of elements, because F is a fixed field of odd K over F. And by definition, this tells us that the field extension is Galois. So the field extension will be Galois, provided that F is a fixed field of the group of automorphisms over F. But this is not always true. So if we take Q adjoined the cube root of 2 over Q, then the fixed field of the group of automorphisms over Q, since the group of automorphisms over Q is just a trivial group, the fixed field is the entire extension Q adjoined the cube root of 2. But so it's not Q, so it's not by this criterion. I can't use it to deduce that it's Galois, and in fact, it's not Galois. Okay. So thanks for listening. Okay.